So here's our objective. Sorry, here's our topic. Here's our objective. And by correlate, that means like connect and explain why, how these things are all related. And we've got these two molecules. It's going to mean something about the bonds themselves. All right. Particularly, what does the bond order tell you about its energy and the bond length? Right. This is topic 2.2. Okay, we're going to flip around. All right. So you look, I've got three different types of bonds here. I've got a single bond, a double bond, and a triple bond between these carbon atoms. What does that mean about the length of the atoms, the lengths between the atoms? Now, you can kind of see it here. The carbons tend to get closer together, and the more bonds that you make, and it also means that the bonds get stronger, all right? And by stronger, it would take more energy to break them apart. Okay, so for your bonds, here's what they look like. And all right, that's the Lewis structure. I'm leaving out lone pairs, but that's kind of what they look like. The type, it's single, double, and triple, all right? And the order is first, second, third. The order is the number of bonding electrons minus the number of non-bonding electrons uh, divided by 2. And we're not going to get into the theory part of the order within this video. If need be, I'll save that for a different video. And the length, in general, these things should increase, or sorry, so should decrease like we saw in the models. So it goes from the longest to the shortest, and it goes from the weakest or the least amount of energy to break to the strongest to the most. Now, this is, I'm going to flip my camera around, so let me pause it. All right, you can see right here, this is average bond energies. This is from TRO. Here's carbon single, double, and our single, double, triple, 347, 611, and 837. So you can see as it goes from single, double, triple, the bond's energy goes up. So it goes from weakest to strongest. And if you look over here, the bond length from single, these are nitrogens, the bond length goes 145 to 123 to 110. So the bond length decreases. All right. Okay, those values came out of the TRO book. Now, there, there, there is an important note in that uh, for resonance, and with resonance, you're going to take the average. You can see here, I didn't animate this slide. You can see with this sulfur, it's got a single and a double, but then it's got a resonance structure. So it's kind of every bond is flipping back and forth between the single and double. Well, for this case, you just take the average of them. So there would be the bond order here would be 1.5. All right. Now here's another example. This is the nitrate molecule NO3. You can see that there's the potential resonance structures where this double bond is rotating from here to here, and then it's going to rotate between the bottom, right, and vice versa. So you take like the average. I've got 3 bonds, two are single and one's a double. What's the average of that? 1 and a third. All right, so its bond order is 1 and a third, or 1.33. Now, what this means in terms of NO3, this is the chart from before. Its bond order is right in the middle, right in here, or not the middle. It's actually, since it's 1 and a third, it's more towards the single. You would expect it to be shorter than a single bond, but not as short as a double bond, and not as strong as a double bond, but stronger than a single bond. All right. And that's just what I said just now. Now, to go back to what this means, like here I've got oxygen gas and I've got hydrogen peroxide. Well, oxygen's gas, if you did the Lewis structure, it's going to look like this. And if you did it for peroxide, it would look like this. Therefore, you'd expect this bond to be shorter, have more energy than this one. These are shorter than both of those because hydrogen, it is a smaller atom. And that's why it's shorter. Okay, and that's what this all means. Okay, thank you, and let me know if uh, anything I can do to make it clearer. All right, bye.